Ram now is going to talk about the Semi-Lagrangian Discontinuous Galerkin conservative transport scheme on the cube sphere. Please.
Thank you. Good afternoon. I am going to talk about a Semi-Lagrangian Discontinuous Galerkin method applied to cube sphere. Okay. So I worked with a student, a graduate student from University of Houston last summer. So this is called SciPark project at NCAR. We invite students to work with us 2 or 3 months, and normally our students are very good. They work hard and produce good results. Okay. Motivation of my talk. What you see here is a cube sphere grid with this spectral element gridding, and you can see the blue line separating the elements, and you can see highly non-uniform points within the element. These are actually quadrature points. Okay. This type of grid is a must for spectral element or discontinuous Galerkin methods. So you can see that grid lines are highly non-uniform and non-orthogonal. Discontinuity at the cube face and edges. The green lines are the edges of the face, and these points are the corner points. So the real challenge is how to make a conservative transport with monotonicity or at least positivity preservation property, and that transport should be highly efficient, and that should be capable of transporting order of 100 traces in a realistic climate model. The transport schemes with the spectral element or DG are just fine, no problem. But if you consider the high efficiency, that is going to be a burden. You cannot transport 100 species or more than 100 species with the spectral element transport scheme, or DG transport schemes can be very, very expensive. So a way to get around is use a Semi-Lagrangian idea. Okay. So a possible remedy for this one, use finite volume Semi-Lagrangian type transport. For example, C-SLAM, developed by Lorison et al. And as implemented in CAM. So which uses a finite volume grid overlaid to this kind of grid on element basis. And so this is a finite volume based Semi-Lagrangian, so it's conservative. You can constrain to be monotonic, and what you need is actually an interpolation or a remapping scheme between the physics grid, that is the finite volume grid, and the spectral element grid. So you basically you end up with two grids, dual grid system. Okay. So high order transport schemes, there are 2 classical approaches, an Eulerian approach, so which uses fixed numerical mesh in space, arbitrary order of accuracy in space and time if you wish. For example, if you consider Runge-Kutta DG method, so that is very good, but the only trouble is the CFL is very much limited to the maximum degree of the polynomial you are using. This here the CFL is just an estimate, it is not exact. Whereas in Semi-Lagrangian approach, the combination of Eulerian approach and Lagrangian approach is used. The mesh is fixed. Numerical solution is updated by following the trajectories backward in time or forward in time, allowing very large CFL number. So what I am trying to do is combining these 2 approaches into a single framework. Again, Semi-Lagrangian method got its own problem. For parallel communication, whenever the CFL is very, very high, it's not desirable. So it can choke the parallel communication. So my target is CFL something nearby 1, so that my tracer transport scheme will be efficient. Okay, let me go through what is DG method is all about. So consider the scalar transport equation in one-dimensional form like this one. This is a conservation law. So first thing is you partition a domain, one-dimensional domain, ij minus 1, which are not continuous at these points. So for regular RKDG method, discretization starts with multiplying this continuous equation with a test function and integrating over an element. So you end up with this weak formulation. Here phi h is actually the approximate solution you are looking at that solution in the polynomial space, and psi you see is a test function which belongs to a vector space. So at the element edges, you have two values coming from the left and right. You have to resolve it by using a Riemann solver. A Lax-Furedi Riemann solver is more than enough for DG application. Okay, now the discretizing the element, basically for efficiency we use a nodal basis set, which is this form. If I use 4 Gauss Leibovitz-Legendre points, this is the structure of that one. This is not uniform. When the degree goes higher and higher, when the order goes higher and higher, you can see lot of points are coming closer to the edge. It's not uniformly distributed at all. And your approximate solution can be represented as in this form, where hi is the basis function, which is a Lagrange polynomial. Finally, we end up with substituting this into the weak formulation. You end up with an ODE. You can solve this semi-discretized form in a variety of methods. Okay. Now, let me talk something about the semi-Lagrangian, the basic idea. So this was first introduced by, I mean, at least in this name, introduced by Erstelli a few years back in JCP. He used a fully 2D approach that is theoretically rich, but practically very difficult to implement because of the complexity. And recently, Rosmanith and Scheele and Q and Shu, they came up with some kind of splitting approach, strength splitting approach, solving highly nonlinear loss of Poisson equations. So the theoretical nature of this SLDG is discussed in a, and they made a connection with the Lagrange Galerkin method in this paper, Q and Shu. So I follow the method developed by Q and Shu. Basically, I am using a strength split approach to solve a 2D equation. So to start with, let us consider the test function follows the advective form of the test function follows the characteristics, or we can write it this form. And this psi, the test function at new time level, is capital psi here. So this is the basic form. Your solution and test function are integrating over the element, and this is the time derivative. So the weak formulation here translates into this form. There are a lot of steps. I'm skipping all the mathematical details. So basically, you want to find phi at new time level n plus 1. So for that, you have to evaluate this one. In other words, you have to evaluate the integral on the element ij star, which is the upstream element corresponding to the element ij. Okay. So here my task is to simplify this integral. The first step is, you can see here two time levels Tn and Tn plus 1. This is a regular grid. This is the upstream grid, I would say. So first thing is, if you consider this element, you have to backtrack the origin of this at the previous time level, which is not on a regular point. It could be from another element. So this is the 2 points corresponding to these 2 points. The next step is, every piece of this upstream element, which can be broken into multiple elements. So that is ij star is given here. You have to put same number of points, say k plus 1 GLL points, that you can see here. These red circles here. Okay, and yeah, this star denotes actually upstream position of these points. Then they trace the trajectories forward in time from this level to up, new time like Tn plus 1, that you can see green points. This is for evaluating the test function, because we believe that test function follows the Lagrangian trajectory. So you have all the ingredients wanted here. So this quadrature can be simplified in this way. Wm stands for the weights, GLL quadrature weights. This is the value evaluated at the upstream point for every piece of the element, and this is a test function which is evaluated at the new time level. This is the width of the element. So that's the core idea of the semi-Lagrangian DG. Okay, now we have to find the trajectory equation. We have to solve the trajectory equation. So here there are 2 operations, that is backward in time, finding the trajectory origins, and from there going forward in time, then backward and forward, there are two operations. This is done by solving this ODE, or you can use a Taylor series expansion, or even you can apply McGregor scheme, or you can use the classical RK method. So I use this classical RK method to find the upstream position and going forward in time. Now I am applying a filter. This is a very cheap filter recently developed by Shang and Xu, and which works really well for spectral element grids. So imagine Pij is your solution at no time level, which is oscillatory and which has negative values. So you don't want to see the negative values in many tracer equations. So this is the filter applied. The P till I is actually the limited or cleaned up solution, and which is actually subject to the conservation law. So this limiter won't take away the conservation property. Here what you need to know is the cell average of the solution, that is Pj bar, that can be easily determined, computed. M star stands for the minimum value from this element. So entire operation is on a local element, so it's very efficient. Okay. Next, how do I go from 1D to 2D? So 2D transport equation is given like this one. So I apply a strand splitting, that is a dimension splitting here. So this is relatively easy to implement, but the downside is here it is only accurate delta 2 squared accuracy in time, and you have a sequence of two equations. So this is along x and this is along y. So first what we do is take an element, you sweep in x direction, find the intermediate solution, then go in y direction. So the trajectories are determined by solving these two equations. Now I am going for some test results. The first one is a new test by Blosier and Duran. This is a very interesting test. This is a deformation flow test of a cosine bell or a cosine distribution on a 2D Cartesian domain. Initial distribution deforms into a crescent shape and comes back to original form. The final analytic solution is known at the final stage. I use a 60 by 60 elements, and with a CFL 0.95. I could have gone to CFL 2 or 3, but this is my interest, which is 6 times larger the maximum times permitted by RKDG method. So the BP filter is the monotonicity filter is used. Okay. This is the initial position of the cosine bell or the cosine distribution. The black line indicates the analytic solution. 1/4 of the simulation, it forms into a tiny filament. Blue thing you see here is blue lines are actually zero contours showing lot of oscillation, and half the time step it comes back to the original position, then the course turns the other way around and finally reaches to the original position. So this is the solution. After applying the filter, okay, I get the solution like this one. Okay, we check the accuracy of L1 L2 norm, that is actually not affected by the limiter, which is very good, and this is the smooth solution, and here you can see the analytic solution and the numerical solution matching very much, and we compared the result with many published results. Those are very satisfactory. Okay, now extending the idea to the Cute sphere. So we use actually equiangular projection proposed Ranchik et al. The conservative form or transport equation is, this is the transport equation on the Cute sphere. Square root of G is the metric term associated with that, which is analytic and it's known. So if I combine the metric term with the contravariant form of the velocity, I can make the flux in this form, so I can write it very, very conveniently. So this is just like Cartesian. So this is the logical pattern of the Q phases, 6 phases aligned like this one. Okay. Now this is a GLR grid embedded on the Q sphere. So I do my SLDG advection along these lines, followed these lines. However, whenever I get into the edge, I have to find, I may need an halo point. So I just extend the points by extending the lines to the other face. You can see the red points here and blue points left. So this is a kind of extending the grid lines. So I solve the trajectory equations along the grid lines using the contravariant wind. So I can find upstream position x1 direction followed by x2 direction. Okay, now some results with the classical test. That's the solid body rotation. Maximum value is 1000 and minimum value is 0 after one revolution along the northeast direction. That means 4 coordinates and 2 edges. So you get the solution without limiting. This is a maximum value and it's a minimum value. When I apply the limiter, you get a clean solution. So here I use a time step of 1 hour, and L1, L2 arrays are comparable with the DG solution corresponding with the same resolution, but delta T is 5 times larger than the RKDG. However, L infinity error is larger for SLDG due to the splitting error that I can show in the next slide. This is a time traces of the arrays L1, L2, L infinity arrays. Here, these two are actually without the filter. This is with the filter. With the filter, actually improves the error measures, and here you can see which is L infinity error. It's very trivial. It crosses through the 4 points. You can see the because of the split error, you can see the oscillations there. And when the flow is along the equator, you don't see that one. So it's very, very clear that there is some problem with the coordinates. Okay. However, if you see the maximum value of this oscillation, it goes something between 0.02 and 0.3 and stays like that. And if I compare a finite volume method by Lawrenson et al., this monotonic case, you can see this is a comparable resolution. You can see the L infinity error goes this way. So I would say that these two are comparable qualitatively. Okay, this is a very crude comparison with the RKDG and SLDG. So I use these time steps here and showing how fast is RKDG compared to the SLDG. And here the flow is along the equator, so SLDG really is more accurate than the RKDG. For the case along the vertices, when the flow is along the vertices, that means northeast direction, you can see SLDG is lose the accuracy because of the split error. So in general, SLDG is more computationally efficient than RKDG for a given order of accuracy. Now there is another test which is a vortex rolling up and coming back to original position. The advantage of this test is analytic solution is known at any time. So here the field is non-zero everywhere, and you can see the error plots here. L infinity error is slowly going up when the flow is along the equator. Here it is more noisy. So that again we compare the result with the published results, and which is very well comparable. This is another tough test. So this is designed to challenge any advection scheme on the sphere, and this is the initial position. The 2 slotted cylinders goes to this very tiny filament formation and comes back to the original form. And here you can see some diffusion is happening here, but I compare the results with many of the published results, and it's very well comparable. And again, the time step is much larger than the regular DG permits. Okay, now my conclusions. The semi-Lagrangian discontinuous Galerkin scheme has been extended to Q-sphere geometry. SLDG employs a sequence of 1D operations to solve 2D transfer problem. Is a split method. The scheme is accurate, positivity preserving, and can be significantly lower the time step as compared to the RKDG method. So the computational overhead associated with finding the trajectories can be maybe negligible if you want to transport hundreds of quantities, such as in CAM home model, NCAR's CAM model. SLDG with CFL nearly equal to 1 is a viable option for multi-tracer transport on spectral element qubit sphere grid. No need for the dual finite volume grid. Tracer transport and dynamics can be made very consistent. So future work is to analyze what is going wrong at the corner points, how to decrease the L infinity error, and if possible, if time permits, if funding permits, apply SLDG scheme to shallow water irrigations and oil system, etc. And these are the results. Whatever I showed is the preliminary results. We are doing more experiments on that, and that's all. Thank you very much.
Is it still conservative if you don't do the integration exactly? So you're kind of doing the quadrature to some.
This is integration is not exactly. If you do the integration exactly, what I found that in the Q-issue paper, there is some kind of instability in nonlinear flow. They have shown some.
Okay, but is it still conservative if you?
This is exactly conservative. If I start everything is flux flow, that is my first priority. If it's not conservative, I won't touch it.
Okay, I didn't really see from your formulas how it could. There wasn't a. Can you show me where the flux is?
Yeah, sure. Okay, I think somewhere here. Okay, this is a test function which is not conservative at all. Okay, this is a primary variable. Okay, phi is the field I'm addressing. So, which is actually in this formula. Sorry. Yeah. On discretizing that, you get into this form. I'm skipping the details how you go to this form. And here phi n is the new time level, and this is integrated over, numerically integrated over the upstream element, which is a union of several fragments of elements. And everywhere, so this is the final formula for that.
Okay, so you're subdividing the bits of elements and then do and then undo.
Yeah, I'm subdividing the elements. So you have to find, this is I am tracking back the element where it is coming from. It may be union of some subintervals. So I am putting same number of quadrature points to keep the order of accuracy, k plus 1 grid points as DLL points. Then I have to find a test function, But test function follows the Lagrangian path. That means I can use the value here if I go this way.
I see how it's conservative.
Then I plug it back, so it works fine. Thank you.
Further questions or comments?
Are there any issues with it being consistent with the mass conservation equation from the dynamics?
Actually, I didn't check with the full dynamics. It's only
Right,
isolated.
but you can anticipate them because this transport scheme is not the same scheme that will be used time integration wise to update the mass. And for example,
Yeah, that
yes,
would be
something like that.
I understand, and that would be a problem because if I put this on home is using a different time stepping, and for the tracer transport, I am using maybe a different time stepping. So that's a practice in CAM. So I don't see this a problem.
But in, for example, the FV core, they time average the mass fluxes in order to maintain consistency between the tracer transport and the mass, the conservation of mass in the solver. So they do maintain that consistency. Do you see a similar mechanism?
I think it's possible to make in that way. So it's possible because here the only velocity field is predicted by the dynamics, right? It's using the same identical element. So there is no overlaid grid or anything. So everything is living in the same space, polynomial space. So I don't think there should be a problem. I'm not sure exactly. That's what I think. There could be some kind of inconsistency. I'm not fully, I don't know about that.
This sounds like for a conversation in the coffee break, which as it happens starts right now. We'll thank the speakers and